Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, the International Telecommunication Union. Today, we are having another exciting webinar, a challenge finale for radio resource management for 6G INX subnetworks. This webinar serves as an ending webinar to the challenge, and during this webinar, we will review the challenge problem statement, present the solution of the winner, and share some extension works to this challenge. But before officially kicking off this session, I would like to introduce our esteemed speakers, Saeed and Pavan. Saeed Hakimi is a postdoctoral research fellow in the Wireless Communication Network section of the Department of Electronic Systems at Aalborg University. Saeed is the organizer of this wonderful challenge. And Pavan, who is the winner of the challenge. Late congratulations to you, Pavan. So Pavan is the research engineer with Nokia Bell Labs France. His research interests lie in the intersection of signal processing and machine learning-based algorithms for the physical layer and the MAC layer for 6G networks. And my colleague Vishnu will be taking care of the Q&A session. Now, without further ado, I would like to pass the baton to Saeed. Saeed, the floor is yours.
Thank you very much, Jiaying. Just a moment. I share the screen. I hope you can see my screen now.
Yes, we can see your screen. Please
Yes.
present it.
Yes. Perfect. Hello, everyone. Nice to meet you and all here. And then I hope you have a nice day today. Today, we are going to have our finale on radio resource management for 6G INX subnetworks. Actually, about the initiation of the challenge here in the wireless section network of the Aalborg University, we have lots of projects. Actually, 2 of them, which was EU projects, 6G Shine, which focuses on key technology components for INX subnetworks. And the Centric project leverages AI techniques through a top-down modular approach to wireless connectivity. So the convergence of these 2 EU projects is this challenge. Well, in short, about the challenge, 6G INX subnetworks are short-range and low-power cells for entities like robots, vehicles, production modules, classroom, and etc. In general, the use cases and scenarios can be categorized in 3 groups: industrial, in vehicle, and consumer subnetworks. So as an example, for the industrial, we can name fast closed loop control or robots and production modules. For the in-vehicle, we can name motor control, braking, ADAS sensors. And for the consumer subnetworks, we can name XR applications for education, gaming, and entertainment. Actually, one of the main challenges for the 6G INX subnetworks are radio resource management. We have different strategies, centralized, distributed, and hybrid. And about the consideration of the challenges, we can have the interference, legitimate interference and malicious interference. And about the deployment, we may have static or dynamic deployments. So in general, the objective of the challenge was develop AI/ML-based radio resource management in hyperdense deployments for industrial subnetworks. So the use cases in industrial subnetworks. So which domains we are focusing? Subband and power. Why? And why they are pivotal in the optimizing the 6G unique subnetworks. Actually, subnetworks lead by nature to high dense deployments, and they can be mobile at the same time. And the performance requirements in terms of latency and reliability is significantly strict. So why the time domain is not suitable for the optimization? Because as I mentioned, subnetworks should support low latency services. And why the spatial domain is not useful? Because the limitations of the access point and specialty devices about considering using the antenna for these, let's say, cost efficient sensors. So they cannot support, in some cases, the multi-antenna. So what we are doing is dividing the available spectrum into subbands, and then controlling the power. We are trying to minimize the mutual interference. So for the moment, I'm not going through the details of the problem. Just very short. The input to the challenge, let's say, is the channel matrix gain, and the output is the individual subband selections and the power level for each subnetwork. So the approach is to utilize the any AI/ML techniques, and then the evaluation criteria that we have done was based on the rate at the median, and then rate at the 10 to the minus 3 power, 10 to the minus 3 probability. And beside that, we also considered the computational complexity of the proposed solutions. After evaluating different solutions, different, let's say, submitted solutions, we selected the solution by Pavan Koteshwar. Congratulations to Pavan. I think, as far as I know, he's also going to discuss about the details of the evaluation and all of the required technical aspects. So I will give the floors to Pavan to.
Yeah, thank you, Said. Am I visible?
Yes, I think.
Can you hear me?
Yes.
Okay, great, thanks. So shall I share my screen?
Yes, just a moment. Yeah, I think you can. No.
I think you need to stop sharing before I start.
Okay.
Yeah. Okay, probably now. Okay, is my screen visible in full screen, full mode?
It's not in full, but it's visible.
Let me know once it comes up, and I'll begin.
Pavan, I think it's okay if you just present the slides and they will be in full mode.
Yeah, I'm sharing the slides. Are they not visible?
We can see your slides.
I can. Okay. So yeah, thanks very much. My name is Pawan, and I am a research engineer at Nokia Bell Labs France. I work mainly on the physical layer and the MAC layer aspects of communication systems, and we evaluate all sorts of techniques, ML based or classical. So yeah. And I would like to specifically thank Saeed for having organized this challenge very well. And in fact, after the challenge, he approached me with, and we had a successful collaboration as well, which he'll talk about later. I would also like to thank Jaing for inviting me to speak here. And so, yeah, let's commence. So this is the agenda. I'll briefly describe the problem and the proposed approach, and then
Pavan,
yeah.
Sorry, we can not see your slides moving. It's still on the
Oh,
first
okay.
slide.
I have gone to the second slide. So let's see. Now does it?
Yes.
Okay, I cannot go to full screen, I suppose. So I have to remain in this mode. Is that okay?
Yes, please.
Yeah, okay. So yeah, it'll be in this mode, not in full screen. Um, so the agenda is as follows. Um, I will briefly describe the problem and then the proposed approach and then the winning solutions. We evaluated a couple of techniques and I will compare them and present the winning solution and the results as well. And some key takeaways before handing over the floor back to Saeed for him to present the extension of this problem. Okay. So we have, yeah, we have this in-X setup where it could be an in-factory subnetwork system. You have several subnetworks. Let me see if I can. No, I cannot. Okay. Uh, so shown here are subnetworks 1 to n, and then each subnetwork has a wireless access point and a wireless device that it serves. I mean, of course, this problem can be extended to having multiple devices within a subnetwork. But yeah, for this problem specifically, there is just one device per subnetwork, and the transmission is on the uplink. So the green arrow shows the desired link between a wireless device on subnetwork I to its access point. And the red dashed arrows denote the interference links between the transmitting device on one subnetwork and the access points on every other subnetwork. So these subnetworks are connected to a central RRM unit or via perhaps a backhaul, which through which uh, the RRM unit has knowledge of the channel gains of all the subnetworks, and then assigns takes decisions on how to assign the resources based on the channel gains. So the notation is going to be as follows. By n, I denote the number of subnetworks in the system, and here in this specific challenge, it is 20. But this n will be used throughout the talk just to motivate the problem. And each subnetwork consists of a single access point and a single device. So as I said before, the uplink transmission is considered, which each device transmitting data to the access point within its subnetwork and causing interference to the access points in the other subnetworks. So by K, I denote the capital K, I denote the number of available subbands or channels for wireless communication. And in this particular challenge, K is taken to be 4. But yeah, K is used just to denote the number of subbands in general. And the requirement is that only one of them can be assigned to a device for data transmission to its access point at any given instant of time. And as I mentioned earlier, there is a central RRM unit which has global CSI knowledge somehow, and it enables the optimization of this radio resource allocation according to some key performance metric. And this key performance metric is what I'm going to motivate in the next few minutes. So the notation is going to be as follows. By G of Kij, which is real valued, we denote the channel gain between a device in subnetwork I and the access point in subnetwork J. So yeah, and this is on subband k is equal to 1 to k. So let the P and naught denote this effective subband noise power, and PKI is the transmit power for the device on subnetwork I on subband K. As I mentioned, we have a requirement that only one of the subbands can be used for communication. So we'll get that. The maximum transmit power is Pmax. In this particular challenge, it is 1 milliwatt. So with this setup, the realized device rate, which is normalized by the bandwidth, so on subnetwork I is given by this expression here. So it's just the numerator is the transmit power on for device I, and the channel gain from device I to its its access point on its own subnetwork, and the interference is the the transmissions from the other devices in other subnetworks. So device J to the access point in on subnetwork I, and the noise power. And here is the requirement that so I here denotes the indicator function, So it's which is 1 if only if the power is greater than 0 on that subband. So we have a requirement that out of the k subbands or subchannels, only one of them can be used for communication at a given instant of time. So this is the setup. And as Said briefly touched upon, the evaluation metrics is composed of two submetrics. The first one is the median rate. So the median rate is, of course, it's an indication of the system level capacity. And then the 0.1th percentile, which is denoted by P0.1. So this measures the bit rate at very low percentiles, assessing the system's performance under extreme conditions. And yeah, the weakest users' performance are often one of the key metrics in any wireless communication system. So the performance score as given for the challenge was omega 1 times the normalized rate at median plus omega 2 times the normalized rate at the 0.1 percentile, where the normalization is done across all available solutions. So if omega 1 was taken was given to be 1 by 3 and omega 2 2 by 3, so the emphasis is more on the weakest users rate. Now let's move on to the problem formulation. So the task is to find the optimum power allocation, so as I explained earlier, subscripts k comma I denote the transmit the power from device I on the kth subchannel. So we need to find the optimal values of this, and that's given by this. Those values are the ones that maximize this particular function here. So we have n subnetworks. So the sum of all of them and the function of the rates Ri of each device on each subnetwork, such that there's only one subchannel allocated to a user device. So now f is can be taken to be some suitable alpha fairness function. As an example, alpha if alpha is equal to 0, it's the arithmetic mean. Alpha is equal to 1 is the proportional fairness or the geometric mean. And for this particular challenge, as we note that the highest weightage is given to the weakest user's performance, it's desirable to use the max-min function, which corresponds to alpha tending to infinity. So with that, the problem can be formulated as shown here. We want to maximize over these possibilities for all subnetworks, the minimum of the rates, such that only one subband is allocated to a device at a given instant of time. So yeah, let's rewrite the problem formulation and as a reminder here and make some observations. So this is the problem formulation, and this is just the rate for device I, and this is the minimization over all devices, and then we need to find the maximum over that. So the first observation is the following: the problem is actually non-convex in the PKIs, even without the requirement of a single subband allocation, and that can be verified by simply computing the Hessian of this objective function and ascertaining that it is actually not positive semi-definite. The second observation is that the optimization problem is permutation invariant to both subband ordering and the subnetwork ordering. That is, for any permutation pi from 1 to k onto itself, and then sigma, right? This is the permutation on the subband subnetwork index. We have this equality here, which means that for any permutation for both of them, the answer should be the same. So why is this important? This kind of eliminates some of the well-known machine learning techniques like using deep neural networks and convolutional neural networks, which are actually very sensitive to the ordering. I will repeat that in the next slide. Yeah, as I mentioned earlier, even for k is equal to 1, the problem is non-convex, which means that you cannot simply use the well-known convex optimization techniques. And further, the task is the challenge is compounded by the fact that only one subband can be allocated per device. So we need to do something smart. And what I proposed was to approach in a two-stage manner. The first stage performs an optimization technique to identify the subband to be allocated for each device. And then following the identification of the subband, the next step is to identify the power to be allocated to each device. So we just split the task into two stages. The first one is the subband identification, and the second one is the power allocation. And to do both of these, we can employ any permutation invariant ML-based method for both the stages. So now let's look into detail about what the stage one is. So let f of theta 1 denote a permutation invariant ML model, where theta 1 is the set of trainable variables. And this model has an input feature of shape k cross n cross n, representing the channel gain tensor G. As I mentioned, G represents the channel gain, which is of shape k cross n cross n, where G k comma k G of k I j represents a channel gain from the device on subnetwork J to the access point on subnetwork I on subband K. So the first stage has two outputs of shape k comma n. The first one is denoted by C here. It takes values from 0 to 1 with a softmax operator operating along the first dimension, which is the dimension that K represents, capital K represents here. And this means that it needs to sum to 1 here. So C of k comma little k comma I denotes the fraction of the power to be split for subband K. The second output is denoted by little P here. This it also takes values from 0 to 1. It's enabled by a sigmoid octave activation function that that represents the normalized power, which is normalized by the maximum transmit power. And P of little k comma I denotes this power for device I on subband K. So training is done in a self-supervised manner. So it's not supervised training. It's self-supervised. So we have this rate expression here, right? And I just if you take out P max, right, that you get and bring it here, you have these fractions as I mentioned here. So each of these takes values from 0 to 1. And then this is basically the rate for user device I, and then we want the minimum to be maximized. So we are having this, we have this negative to be minimized. Now, so this is not the final solution, right? Because the requirement is that each subband, there is only one subband allocated to a device for transmission. So what I've used is instead of that, I've just split the assigned by through CKI the power split across subbands. So the purpose of this first step, as I mentioned, is to identify this best subband to be used for that device. So once we train using this loss, what we expect is to get rates across all the subbands for all the devices. So what we will do after this first stage is to just look at which subband for each device maximizes its rate, and then use that as subband as the allocated as the identified subband for that particular device. So that's what this function does. So by k star of I denote the identified subband for device I. So the second stage is the power allocation. So we need a separate permutation invariant ML model here. So it's denoted by h of 2, where theta 2 is the set of trainable variables for the second stage. It also has the same input feature shape, which is capital K n and comma n. The same channel gain tensor is used, but then we need to use a trick here. So we multiply element wise with s belonging to 0 comma 1, where s of little k comma I comma j is equal to 1 if k is equal to k star of j from stage 1. So if to repeat, k star of j is the identified subband for device k for the device on the subnetwork j. So if that is identified, then this is 1. If not, that it's basically 0. So if you multiply by that, we get a modified or altered channel gain tensors. So which means that some of the interfering links are gone. If you recall the first picture with the dashed red arrows, yeah, some of them are basically gone. And the output shape is of shape k comma capital K comma n with sigmoid activation as before. So h theta 2 of g is the assigned power, which takes values from 0 to 1. It's not the final assigned power, it's the normalized power. So we can multiply it by p max to get the final assigned power for the device. So again, the training is done in a self-supervised manner for the loss. So this is the loss here. So this is the rate as before, but then we have the, instead of just the channel gains, we have the channel gains multiplied by this s of k comma I comma j, which is the subband identification vector, and then that's basically the rate that you get for this device, and you want to maximize the minimum of that, so it's the negative of this is the loss. So the final allocated power is taken to be this value here, which is p max multiplied by the obtained values from the output of this ML model times yeah, if I mean it should not ideally be the case that uh, yeah, power is allocated on other subbands as well, but if that is the case, you just force it to be uh, yeah, would be zeros. So there are a couple of there are probably more candidates, but the ones that I considered, the first one being graph neural networks. So we have the permutation invariance requirement, and also equivariance, which I didn't talk about, but I think it's anyone well versed with graph neural networks know that equivariance is more about node level permutation, so which is required in this case. So when we permute the ordering of the nodes that are represented by the devices powers, we also uh, permute the ordering of the final outputs. So that's basically what require equivariance means here. So this eliminates the usage of DNNs or CNNs. It's not that it eliminates it entirely. We can use some tricks to train using DNNs or CNNs, but the effort in training is increased, because since DNNs and CNNs are not permutation invariant or equivariant, we will need to, the training data needs to be permuted, so we need a lot of data augmentation to train this too. So it's basically that the case of that having more training effort required for this purpose. uh, However, graph neural networks are actually apt for this task. They satisfy both these properties, and there's actually a literature on the application of GNN to wireless communications. Just shortlisted two of them here, the most notable ones. Uh, the first one is by Shen and others, which is graph neural networks for scalable radio resource management, and it actually, as one use case, proposes a solution for the case of k being 1 in this ITU challenge. So that is the well-known multi k user interference channel, for which they've proposed a graph neural based neural network based solution. And then Salon and others have also proposed the GNN for cell-free massive MIMO. So it's actually even grown over the years, the application of GNN for this class of RRM problems. So we have, okay. Yeah. So the second candidate that I considered is very simple. Instead of using GNN's f theta 1 and h theta 2 to predict the vector or the tensor p taking values from 0 to 1, we can actually directly model the assigned powers as variables and perform stochastic gradient descent to perform the two-stage optimization. So the first stage will have variables pki and theta, along with a softmax operation on the thetas. Uh, and this is how it is performed. So this represents the rate for user I, and we want to maximize the minimum among all the users. So this is the loss function. So if we look at theta I represents the fractional split that I talked about in the previous slides as well. So yeah, this is the rate, and the first stage is simply to identify the subband, which is done as before. And the second stage is to find the optimal power, or not optimal, let's say the best power that you can find for this technique, and that's done using stochastic gradient descent as well, where this loss is minimized. So I will elaborate this using this flowcharts here. So the first stage is subband identification, where we start with by initializing the little p k comma I with zeros, and then we have this set of variables, trainable variables. Well, I say trainable because they are the ones that are going to be optimized. So it's not like we use any kind of non-iterative approach. It's an iterative approach here. So if you look at the second block here, it consists of three terms which are multiplied. The term showed here is actually this with the well-known sigmoid function, right? So, so what this does is that it ensures that the value is between 0 and 1, and the second term here is the softmax, right, over the sub channels here. I've also used a temperature tau. So if you look at this term in the denominator for this softmax, it's the temperature. So the purpose of the usage of temperature is very simple. If you set the temperature to be very large number, it actually favors a random uniform distribution. Whereas if it tends to 0, it tends to favor a point mass. So the purpose of using a very small tau here is to kind of force this assignment to favor one particular subband. So yeah, so the final allocated the power to be used for sub channel K on device I is the product of these terms, which you can notice that is actually lower than Pmax. And the sum over all subbands is also less than Pmax. So this is the rate for subband for user I on subchannel K. And then the rate for user I is the sum over K, all of the subbands. And then we wish to maximize the minimum of all users, and this is the loss function that is used. And then gradient descent is performed in each epoch, and until a stopping criterion is reached. So the stopping criteria could be either desired a targeted number of epochs, or it could be a targeted tolerance level. And until then, this algorithm is run. And then at the end of the stage, we get we identify the subband to be the one that maximizes the argument over the RKIs, right, for each device. So that's the first stage. And then the second stage is power allocation, where we reinitialize the PKIs to be 0. And then there is no subband identification to be done anymore. We just use the subbands identified from the first stage. And I mean, I've just denoted it using the indicator function, but in practice, it would be using a one hot vector. And then we assign the powers, and again, the similar way to calculate the rates for each subband, and then the overall rates for each user, and then maximize the minimum overall devices using this loss function here. Continue with the gradient descent approach until the second stopping criterion is reached. And then the final allocated power is simply this. So it can be verified that it satisfies both the requirements of the challenge, which is that just one subband be allocated per user device, and the maximum being Pmax. So there were two candidates. The first one is uses graph neural networks, and the second one is direct stochastic gradient descent. Graph neural networks are non-iterative, which means that it's a one-shot answer. Direct gradient descent based approaches are iterative and also non-deterministic, which means that depending on how you initialize the seeds, you can get different approaches, different answers. But let's look at the results. The goal of the challenge is, of course, to get the best numbers, right? So the results are as follows. just to reiterate, the Pmax is taken to be 1 milliwatt, which is 0 dBm, and the noise figure is 5 dB. Noise power per hertz is minus 174 dBm, so which means that the effective noise power per subband is minus 99 dBm. I trained using a graph neural network which used 158,000 odd trainable parameters in stage 1 and close to 80,000 trainable parameters in stage 2. And this training was done on the initially provided training data set. And the direct stochastic gradient descent approach used softmax temperature of tau is equal to 0.0012. And this value of tau was arrived at by fine tuning on the data set provided with 1,000 epochs per during runtime. So just one observation here: for each sample, each batch, this direct SGD approach requires, because there are 20 subnetworks and 4 subchannels, only 80 variables per stage to be directly optimized. So that's something to note, and I will talk about this a little later. So the comparison is shown here, the numbers. So this is the model. GNN has a median of in bits per hertz per channel use of 6.97, and the 0.1 percentile being 1.26. Whereas direct stochastic gradient descent approach, it has a higher median, not by much, but yes, it is higher, but a significantly higher P01, and that shows that it's actually quite it performs really well for the very weakest users, and that's really what we want. So if we look at a comparison between SGD, direct SGD, and trained neural networks, and then if you look at the attribute, so what is marked here in bold is the desirable attribute. So as I mentioned, trained neural networks are non-iterative, which is desirable, whereas SGD is iterative. Uh, with regards to the inference speed, there is actually 2 ways to look at it. If you look at the small batch sizes, right, less than, for example, 1,000. I think in my system it was 1,000, but it could be something else in the RRM, your central RRM unit. Uh, so trained neural networks are obviously faster. However, for large batch sizes, uh, because the trained neural networks require more number of trainable variables, so it's a memory issue, right? They can't really handle all of it in one batch, so they need to be split into mini batches. There I observed that direct SGD is actually faster than GNN itself. And if you look at these results here, of course, what is shown here is just one realization of a GNN. If you increase the size and smartly fine tune it, it could actually probably give better results. But I didn't find any case where it actually beats the SGD, direct SGD, which means that the training effort is actually significant for neural networks, but whereas it's very little for SGD. And then the memory is again very low. As I mentioned, it only requires k times n variables per batch. So it for the same memory, this can actually perform much faster and give much better results than a GNN. Okay, so the key takeaways from this study, right, is that in general, direct SGD based optimization has the potential to play a crucial role in wireless radio resource management. Especially when we have this something of this form where it is non-convex, and it is a little tricky. It's not a direct, straightforward non-convex optimization techniques are not possible. So the advantage is that it's actually simpler to implement than trained neural networks, and provides superior performance, has lower memory requirements as well. And of course, there is a downside. It's non-iterative, which means that there might be some, depending on the computational capabilities of the central RRM, might require more inference time. So that there is always a trade-off involved. Uh, so I would not rule out GNNs in this kind of challenges or tasks, because they do enjoy faster inference speeds for small batches sizes, and are actually also non-iterative, which means that Yeah, it needs to be handled on a case-by-case basis. So further investigation for the potential usage is merited, definitely. So with this, I hand over the floor back to Saeed, who will talk about an extension of what we did. So after this challenge ended, he contacted me, and then we collaborated to work on a problem, and we had a conference paper out of this. So I will hand it back to Saeed, who will round off the presentation.
Yes, thanks, Pawan, for the nice presentation and the innovative, simple, and yet very efficient solution. Just a moment, I can share the screen again. Okay, I think now you're seeing my screen again.
Yes, we can see.
Okay. So, our goal from this challenge wasn't to resolve all of the issues and challenges of the radio resource management for the Unix subnetworks. But our focus was on subband allocation and power control. Actually, after getting the registered solutions, we thought that maybe let's evaluate the solutions under, let's say, more critical scenarios. In the first stage, we had the subnetworks that faced just interference from the inter-subnetwork interference. Let's say they had inter-subnetwork interference, which caused by neighboring subnetworks which operating within the same system. But we may have also external interference originating from other radio technologies coexisting in the same area and sharing the same frequency spectrum. And the point is that about this external interference, they are usually unpredictable, and they are beyond the control of the network operators, or let's say centralized controller. So we decide to evaluate the solution on both under the both inter-subnetwork interference and also external interference. The other extension was about the scenario of the movement of the subnetworks. I mean, in the initial challenge statement, the subnetworks was static, but we tried to evaluate the solution on the dynamic subnetworks. I'm not going through the detail of the algorithm. Pawan already mentioned everything. Actually, as the benchmark, we used two, let's say, iterative algorithms, heuristic algorithms. The first one, sequential iterative subband allocation, SISA, and for the subband allocation, and the second one, sequential iterative power allocation, or let's say SIPA, which both of them iteratively try to minimize the network-wide interference to signal ratio. Actually, originally they are not designed for considering the external interference. So we extended both algorithms by using the, let's say, estimated external interference. I mean, the same approach that the original work was using the input data. We used the external interference the same to have a fair, let's say, comparison. And then about the simulation setup, as I already mentioned, we consider the mobile subnetworks and also the, let's say, external interference is also moving. We have the channel gain is something like this. We have the complex small scale fading based on the Rayleigh distribution. And then pass loss model is based on the dense clutter and low base station height in factory scenario from the GPP model. And then the shadowing was the correlated shadowing. I'm not going through the detail of the simulation setup, but I mean, the number of subnetworks was still equal to 20 and the number of subbands equal to 4. For the external interference, we considered the external interference is the model is based on the Poisson process with the average arrival rate lambda, which I think is equal to 0.3. Yes, here. And then about the power of the external interference, we defined it relative to the maximum transmit power of the subnetworks. So it's related to the power of the subnetworks. And by default, it's 20 dB less than the maximum power of the subnetworks. So here we have the CDF of the average spectral efficiency across all of the subnetworks. So we have two scenarios. Interference on our scenario and interference of our scenarios. We can see that for almost all of the algorithms, the difference between the two scenarios is substantial. So we can see that even with not that much high external interference, we have substantial degradation in the performance. In the right, we have the outage probability of the individual links across all of the subnetworks under different scenarios. We have two extreme, let's say, scenario. The first one is no interference scenario. The other one is the interference on our scenario. So we can see that's two extreme results. And in between, we have interference of our scenario that we can compare the benchmarks and also the proposed solution. We see that, for example, the gradient descent resource allocation, the outage probability is 0.0008, but for the benchmarks is 0.077. So we can see that if the benchmark, the baseline is the CISA-CIPA, we have 90% reduction in outage probability. For evaluation of the effect of the power, let's say external interference power, here we see that as we increase the external interference power, we have more outage probability. Again, as we discussed earlier, for the, let's say, spectral efficiency equal to 3 bit per second per hertz, the proposed algorithm guarantees 99% reliability, but here for the benchmarks, we have a 25% outage probability, which again, the gap is substantial. About the number of subbands which are under the external interference, again, as we increase the number of subbands which external interference is activated there, we have the lower outage probability. But again, we can see that the gap between the proposed solution by Pavan is high compared to the benchmark. Here, we tried to evaluate the transmit power for different external interference power. As we increase the external interference power, both algorithms tend to use higher power to maintain the spectral efficiency. So they are doing the same, but in general, the proposed algorithms use higher powers. And as Pavan already mentioned, the execution time per sample, we compare with the CISA-CIPA. As we increase the batch size, at the beginning when the batch size is low, the execution time is higher per sample. But as we increase the batch size, the execution time per sample is compared to the baseline is less. So this shows the, let's say, parallel processing or let's say batch size processing compared to the totally iterative solutions. So I think that's it. Yes, I think after presentation by Pavan, I tried very short to investigate the impact of the external interference as a new challenge, because in our initial challenge, we didn't mention it. I tried to present the simulation results for the proposed algorithm and compare to some of the benchmarks. Yeah, I think that's it. I would thanks to all of the attendees, yes, all of the audience, and I should thanks to the ITU team for their collaboration to make it possible to have this challenge. Yes, I think that's it. I think we should give floor to the Vishnu.
Yeah, thank you very much, Pawan and the Said, for this very persistent efforts, and also the results. I think they look very nice. I one question which I'm really dying to ask is the the centralized versus distributed. If you remember, Said, there was a lot of research on this topic, anyways. In your studies, especially when you consider this constraints of permutation invariance, have you looked at this problem at all? That certain solutions are more amenable to distributed implementations at all? Does that ring any significance at all in this study?
So I think both approaches has their own pros and cons. So I think when we use, let's say, centralized approaches, we have more computational resources. I mean, but on the other hand, we need to more communication resources. So I mean, it depends, I think, on the scenario and the use cases. I mean, if we have the backbone of the network, which already is equipped with the communication and computation capacities, then I think centralized controller could be the first option. But in some cases, it's not the option. For example, in some scenarios, even we don't have the total CSI channel. I mean, the input is not complete. So what we have is just let's say the local measurements. So in those scenarios, the only option is the distributed solution, I think.
Yeah, I think that is true. That is true. Yeah, and I'm also thinking that in terms of implementing this type of solutions, have you? I think we started discussing this maybe a year and a half before, Syed, if you remember. So have you seen such implementations in the picture? Have you, apart from, I know there are research studies, but in terms of implementations, have you seen these type of solutions be getting implemented, especially considering this kind of incomplete information, as you say? This kind of solutions are in the base stations nowadays. Do you know whether they exist now?
Yeah, I think there are some works that use, let's say, distributed solutions, especially distributed AI/ML solutions for the radio resource management. But I think all of them have. I know that a couple of them have been done in our section, in WCN section. My colleagues worked on these, let's say, types of solutions for the radio resource management, especially for the mixed subnetworks. But I mean, as I already mentioned, I mean, both solutions have their own good things and bad things. So I mean, there are, of course, there are solutions, let's say, distributed solutions. But I mean, for this challenge, we didn't limit the attendees on the type of the solutions. I mean, there were no restrictions. So I think, as far as I remember, mostly centralized solutions had better performance, compared to the distributed one. Of course, there are still much more room to work on this topic. For example, the delay for the CSI as an input. It's not that's always we have the full CSI metrics. Some of them in some scenarios, some of the links are not updated. So that's one of the challenges. Here we didn't consider the energy consumption at all. We had the power, but we just considered the power for controlling the interference, not just the energy consumption. And also here we considered that we always have a full buffer as the data traffic. In some scenarios, when the data traffic is something else, we may have some more efficient solutions for the radio resource management. So that
Very
could
nice.
be that could be some future work, maybe some future challenges.
Yeah, yeah. One last question from my side is, it's very nice that you went ahead and extended the problem statement as well. So how did you select these scenarios? I see that they are quite relevant, but why? What is the reason why you selected these particular scenarios? Can you explain?
You mean about the challenge? The scenario
After the challenge, yeah, the one after the challenge, yeah.
You mean the extension of the actually
yeah.
One of the issues is that usually in radio resource management in general communication network, especially in the subnetworks, we don't consider the external interference, but I think they are always there. And especially for our use case, which are low power, let's say, communication, actually the external interference matter. So that was the reason. As the initial extension, we try to consider the external interference.
Thank you very much. Yeah, it's very exciting to see the closure. Congratulations to Pawan and yourself, Syed. Chang is here. Back to you, Chang.
Thank you so much. Thank you, Vishnu, for the Q&A session, and Syed and Pawan for your contribution during the whole talk. Now, I'd like to thank everyone who participated in this webinar until now. We have more sessions in the future. Please check the AI for Good program page for more details. We look forward to seeing you in the future. Thank you for joining and see you next time.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.